Hi, okay, welcome to another episode of Science and Technology Q&A for kids and others. I think we have a number of questions left over from last week. Let me see, there's a question from Icy. What is my opinion of the usability and programmability of current computers in comparison to ones I've used in my life? Do I have wishes for future computers? Well, okay. So I'm an old guy and I've been using computers for a long time. I first saw a computer when I was about 10 years old, which is around 1970. And the first computer that I saw, I barely saw it. It was in a room sort of kind of tucked away, and it had lots of those, spinning tape drive thingies that you see in old movies and so on. And there were only very special humans that were allowed to go anywhere near the computer. That was a big mainframe computer. Then the first computer that I actually used myself was in 1972 when I was 12 years old. And that computer was about the size of a large desk. And I was fortunate that the school that I was at happened to have managed to get this computer. Actually, one of the teachers there had been a friend of Alan Turing's. Alan Turing was a big pioneer of computing, and somehow through that connection, they managed to get this computer. It was a computer that you can probably find on the web. It was called an Elliott 903C, made by a company called Elliott Brothers, which I can assure you is no longer a computer company. It was actually had been a scientific instrument maker in the late 1800s, and they had got themselves into computers in some collaboration with a company called Marconi. Marconi was a company that was started by the chap who first commercialized radio back around 1900 or so. But anyway, there was this computer, and it was a computer about the size of a desk. It had 8,000 words of memory. So modern computers, usually they measure their memory in bytes, which is 8 binary bits. And usually a word on a modern computer is 64 bits or 8 bytes. That's sort of the basic unit of storage that is used in programs. The computer that I used had 8,000 words. So modern computers like the random laptop will probably have at least a few gigabytes of memory, and if it's a really big crunchy computer, it'll be hundreds of gigabytes. That's so that would be in terms of words, that might be well, let's say 1 billion words of a memory. The computer that I first used had 8,000 words of memory. And somewhat exotically, it had 18-bit words. So normally these days, computer memory is the sort of smallest unit people care about is bytes, which is 8 bits. And as I say, words are usually 64 bits now. The computer I used happened to have rather exotically been engineered with 18-bit words. How did you get a program into the computer? Well, you used usually paper tape. Actually, I might even have one of those paper tapes. Now, you see, this is one of these. You know what? This is very convenient. Well, this is an actual prop. There we go. There's an actual paper tape from the first computer that I used. And it's, you can see it has little holes punched in it. Maybe you can see, there you go. You can see it has little holes punched in it. And those represent the program. How did you read this paper tape? Well, there were 2 ways. One was you could put it in a device that would have little pins, and the tape would be moved through, and the pins would be pushed up where there are holes, and not pushed up where there aren't holes. And that's the way it would be read. The better way to read it was an optical reader, where you'd have a light that shone through it, and you'd have a photoelectric cell that would be on when the light shone through when there was a hole there, and off when it wasn't. And it would go pretty fast. It would go zipping through the reader. One of the big skills in those days was the tape, when it had gone through the reader, would end up in this big wooden bin, and then you would have to rewind the tape by putting it on some winder thing and turn it around. And the trick was, don't tear the tape when you rewind the tape. Anyway, this is a program that I wrote for that computer. It's written in very low level. Well, it's written in assembler. Essentially, the intrinsic code of the machine. So that machine had 16 instructions. So at the lowest level in most computers, like your average, I don't know, Mac or PC or whatever, the lowest level instructions that go into the CPU, typically into the ALU part of the CPU of the computer, there'll be a few hundred kinds of instructions that say things like load this thing into this location in memory, add these two numbers together, do this, do that, do the other thing. So the computer that used this paper tape had 16 instructions, and they had literally numbers. Like the 4 instruction was load the accumulator of the computer, which was a register in a place where you could say, and now this is outrageous that I can still remember all of this stuff, but you could say things like 4 plus 0 meant load 0 into this register in the CPU of the computer. Or you could say, let's see, a 6 instruction was a subtract, and if you said, anyway, it had a bunch of these instructions. I think it would be too weird and boring to tell you what they all were. And the fact is, I don't think I've thought about them in solidly 45 years. So, but I think I can remember them all. Anyway, that was my first computer. It actually ran comparatively fast. It was like every instruction took about a microsecond to run, millionth of a second to run. Had a nice feature. The computer had a nice feature that it actually made a sound when it ran, and so you could tell what it was doing. It would go, you could like hear the program running, and when the program ran into it was in some tight loop where it was just keeping on running the same instructions, it would have this high-pitched whine. When it was doing more complicated things, it would have different sounds. That's one of the features that's gone missing in the intervening years. But anyway, that was my very first computer. Most of the kind of serious computers people used in those days were not computers that a mere human could walk up to and do things with. They were mostly only touched by sort of specialists in sort of tending the computer. It was a very kind of, it's like you kind of imagine in ancient Greece or something, the priests in the temple type thing were the only ones who were actually allowed to touch the computer. And I think the thing that the computer, the Elliott 903 computer that I used, I think its main use was in, I think it was used in tanks and things like that. It was used in various military applications. It was not a particularly successful line of computers. But then within a few years, I started using kind of bigger computers, so-called mainframe computers, usually IBM 360 type computers. That was a computer family that had arisen in the 1960s and was sort of the dominant kind of computer that people used for serious computations. The shocking fact is there are companies that wrote programs for IBM mainframes in the 1960s, and those same programs are still running today. And sometimes they've been running without stopping. And the companies that do, for example, things like credit card transaction processing and things, but they've been running the same program since that time, and they go to tremendous trouble to have the computer never stop, because if it stops, you can't settle the transactions or whatever else. So it's kind of a weird thing. But those kinds of computers, the typical mode of interacting, for example, when I was like 16 years old or something, 1976, I worked at a government lab in England, which had a place called the Rutherford Lab, which had a big computer, lots of big computers actually. And the mode of interacting with them was you would write your program on cards. So the cards were, instead of this paper tape, which has holes punched in it and a card, I'm sure I have a card somewhere, but I don't think I can find it immediately. The cards would be, you have a card punch machine, and you would type what you needed for on each card, and it would come out in holes in the card, and each card was 80 characters across, 80 columns across. And that's why sometimes when you see in modern computers, things are 80 characters, that comes because of cards. But anyway, you would type a card and you press a button and the card would get sort of taken out of the machine and put in a big pile of cards. And so your program will be a big pile of cards. And then you would, the way it worked, you would sort of put your cards in this pigeonhole, wooden pigeonhole type thing. And then somebody would go from the other side, from the kind of computer side, they would take your cards and they would somehow magically run your program on the computer. And then they would give you back a printout, printed on paper by the computer, and put it back in your pigeonhole. And that was the main mode of interacting with the computer. And if you were lucky, that process would take, I don't know, half an hour, a couple of hours, something like that. If there was a bug in your program, it was very frustrating because there would be a whole long cycle of getting that done again. And I think it was so that was sort of a typical mode of interaction with computers, is you hand it to the druids or something that actually dealt with the computer. I'm not sure if they were still wearing white coats at that time, but they might have been. And they would sort of run your program and then give it back to you. Actually, by the next year, 1977, I worked at a US government lab. And that was a time when, I guess, for some reason, they actually trusted the scientists to be near the mainframe computer. And so that was a case where that was, again, an IBM 370, I think, computer, where you could actually, you, like me, could actually be with the computer in the same room, and you could like feed the cards in yourself. And, you know, there were all these flashing lights and tapes and things like that. But you could actually sort of interact directly with the computer, and the debugging cycle got a lot shorter at that time. Although my all-time favorite of that was that you know, you'd put your cards in, you would run your program, something would come back, and there would usually be these error codes if there was something wrong. And I remember there was one, I think it was IEH0321, something. I'm making up those numbers slightly, but it's roughly that. And it's like, what is this error? And there was these big manuals, big books of, you know, error codes for the computer. And so I look it up, and there's all these pages and pages of error codes and all kinds of things. Finally get to the error code that I had. And what did it say? It had only 3 words: probable user error. What on earth were all the other errors? Well, they were all things that might have gone wrong with the computer, not things that were probable user error, like your code is wrong. So anyway, I sometimes use that as an example of people writing software documentation of a very unhelpful kind of thing to have happen. In any case, you know, I think at that time it still was the case that the majority, the results of your computing were on paper. They were printed by a line printer. Line printer just meant that it was printing a whole line of characters at a time. Chunk, 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 big machine that just printed these on this paper. I'm sure I've got a sample of it someplace here. And so those were the results. Now, you know, then, gosh, I'm telling you a whole history of my sort of story with computers, but maybe for some people who are perhaps younger, that's like, there were computers before the way they are today. I think that, well, for me, the next sort of big step, there were these things called mini computers. A mini computer cost only, in those days, probably late 1970s, only $250,000. And as opposed to, which in today's money would be, I don't know, $1 million maybe. It was only the size of, I don't know, several large desks, usually built up a lot higher. Usually those, and so I first had kind of very direct access, kind of was sort of responsible for one of those machines back in probably 1979, 1980. That was a VAX 11780 made by a company called Digital Equipment Corporation, or DEC, which at the time was the world's second largest computer company, after IBM. And I'm afraid, it's a sad feature of the world of technology and commerce that I'm not sure most people have ever heard of DEC anymore. And I know their headquarters were near where I live in Massachusetts. They were in a town called Maynard, Massachusetts. And it was a few years ago that they had a giant factory thing there, and it was demolished. So it was, it's kind of that story is gone. But the next sort of big thing that happened when, for that computer, for example, I forget. Even when I was using a computer at the Rutherford lab, they had these things which used to be called VDUs, visual display units, which meant instead of always just typing your stuff on cards, you could actually have a visual display of your programs and other things interacting with the computer. And you could use a time-shared computer system, which meant that it's kind of like the cloud today. It meant that instead of you just writing your programs sort of offline, you would write them as you would do things where you used a text editor and you typed you typed onto this with files which could be displayed on this visual display unit. And usually those were 80 characters across by 24 characters down, and they had individual characters. It wasn't like the modern displays, bitmap displays, where every pixel can be separately colored red or green or whatever. These were just, it was made with a CRT, like an old-fashioned television, and the electron beam in the thing went, it was a big thing, and the electron beam would go from the source at the back, and eventually it would hit the screen and light up the screen. And the pattern in which it would light up the screen was determined by whether the electron beam had been routed through the so-called character. Basically, they would have a mask where they have the shapes of the characters there, and depending on where the beam was sent, it would go through the place where there was an A sort of template or a B template or whatever, and then be sent to the screen, and that's how it would generate all the characters on the screen. Anyway, so that was kind of the mechanism, and there were starting to be these time-shared operating systems where lots of people could connect to the same computer, and you could do these things interactively like that. In fact, for a long time, by the late 1970s, I was in the US, and I used to use that VAX 11780, and I was usually because you could have this terminal sort of separated from the computer. One thing you could do was just take the terminal home and connect to the computer. How did you connect to the computer? Well, you connected through phone lines. How did you connect to the phone lines? Used an acoustic coupled modem. So what that meant was, the phone is used to sending voice and so on, but it had been figured out how to send, weird tones and so on that represented the data that you were trying to send from the computer. But the technology was, you took a phone, the handset phone with a big, big old-fashioned, wired phone with a big handset, and you literally take the handset and put it into this object that had these rubber cups where, there was the speaker and the microphone were, put into those two rubber cups. And if you pulled the thing out just a little bit, you could hear it whistling. You could hear the computer sending data, receiving data by making different whistling sounds. And usually that was going at about 30 characters per second was a typical speed, and then it increased to about, about 100 characters a second. So actually, I was very impressed with the American phone system, because I connected one of those, and I just left it connected for like 6 months, at my house, and just had the thing connected to the acoustic coupled modem, and it didn't drop any bits. It was just sat there, I don't know, maybe I did something terrible to the phone system by doing that, but it seemed to work rather well. But anyway, then after that, kind of the next evolution was, actually my first company was a software company started in 1981. One of the goofy things that was done by the management that I brought in was they had the idea, gosh, our software has a hard time running on the current generation of hardware. We'll we'll build our own hardware to be able to run the software. And I was like, this is a very bad idea. There were all kinds of reasons why that was very difficult, but it just so happened at that time I happened to have visited Stanford University once, and a chap shows me this computer in kind of a cardboard box that is was called the Stanford University Network Computer, SUN computer. Subsequently became called the Sun Workstation. There was a company called Sun that is now part of Oracle that sort of pioneered this idea of so-called workstation computers, which were intended to be things that were used by a single person as kind of a thing that they would actually do computations right there, for themselves, so to speak, on their own computer, rather than sending it to some central computer. And they also had bitmap displays, that is, displays where you could put arbitrary pixels on the screen and so on. And that those sort of came into existence by maybe 1983, 84-ish. There were a number of companies that sort of competed in that market. I mean, meanwhile, there were personal computers. The Apple II had come out in 1978 or so, even, I think. Then the PC came out, and then the Mac came out in 1984, famously. But those computers, for me, as a kind of a user of sort of more serious computing things, I never really used those kinds of computers. I tried to get portable computers. There was a company called Compaq, I think now part of Dell, that made a very early portable computer. It was, no, actually the very first one I had was made by a company called Osborne. There's a computer called the Osborne 1. It was about the size of a small suitcase, and you could, but it was portable. You could pick it up, you could carry it around. It was kind of an interesting adventure, carrying it through Los Angeles International Airport as probably one of the first portable computers that had been seen on an X-ray machine. It was also interesting figuring out that like if you flew on a 747 plane, there was an outlet right at the back of the plane. It was just one outlet where you could plug the computer in because it didn't have batteries. It took way too much power. But that computer, for example, was it used floppy disks, and it used an operating system called CPM, which was a rather primitive operating system. Really, you could do a little bit of word processing on it, but that was about all that I could use it for. Anyway, I think I'm giving a very long answer to this question, but by sometime in the early 80s, I was kind of using these workstation computers, and honestly, fundamentally the configuration of what's sort of on my desk isn't much different. I mean, the screen's gotten bigger, the computer's gotten faster, at least it did for a while. The operating system has gotten sort of smoother, but the idea of having windows on a screen and so on, I was already using those kinds of things by the early 1980s. Sometimes I would, all these ideas, like when I first saw, I think probably around 1979, 1980, I first seeing the idea of windows on a screen. It's like, you can't be serious. There are situations where you're trying to get a file from here to there, where you're trying to drag it from one part of the screen to the other, and another window is obscuring it, and you're not going to be able to do it. And you have to move these windows like a physical thing to be able to move these files. And I thought this is just going to be a killer misfeature, but it's turned out, well, it's kind of annoying. Every time that happens to me, of this sort of, I just can't drag the file because the drag location, the drag destination is obscured on the screen. I kind of think back to the fact that I thought this was never going to work at all, but it's obviously worked much better than we expected. But back in those days, I could talk a little bit about how one programmed computers in those days. But the main conclusion was that I needed to build my own tools for using computers, and that's kind of what got me started on building computer languages and computational languages and all these kinds of things. I can talk about that more, but maybe I should. I should say that it's always interesting, when you've sort of been around the computer industry and computer technology for a long time, it is amusing the extent to which people say, oh my gosh, there's this new thing. We're now doing this. And it's like, actually, that was something everybody did 25 years ago. You've just forgotten. So for example, the move to cloud computing is just the same story as the whole time-sharing story from back in the distant past. It's and even, you know, for example, I first had email in 1976, there were computer networks. I used to use the ARPANET, which is an early predecessor of the internet, and I used that starting in 1976. There were only, whatever, 256 computers on the ARPANET at that time, and each one had a number and so on. But it was still sort of the same idea as today. But this trend between sort of, are you going to do it locally? Are you going to do your computing locally on your local machine, or are you going to do it on a big distant machine? That trend has been going back and forth for at least 50 years. Of, you know, is it local? Is it remote? And it's really a question of the relative, you know, how fast is the computer? How fast is the communication channel? How much stuff are you trying to send back and forth? How well can you predict what has to be sent? You know, if it's a movie, you kind of know in advance you're going to watch the next 5 minutes, so you might as well preload that and so on, those kinds of things. You know, it's always interesting to see these different styles of computing that become popular. And I think, you know, everybody's been waiting for virtual reality and augmented reality and so on. I remember I first probably used a VR system probably late 1980s. And everybody said, it's almost here, you know, something where you can kind of see the, you have head-mounted display and so on, and you can kind of get a realistic view of the visual scene. Well, it's still not here now. You know, will that be a way that I choose to use computers? You know, I have to say, apart from the fact that I have tried using VR for some of the things I've been doing in our physics project, I get a little bit, I still get a little bit seasick, motion sick or something when I use these things. That will probably improve as some of the tracking gets better for those kinds of devices. But you know, it will be an interesting time when there's a very different way to write programs and so on. That's a really different environment from the one that basically I've been using since the early 1980s of, you know, Windows on a screen, etc. You know, I've been trying to build sort of computational language that brings us to a much higher level of what we can expect to do in interacting with the computer. Hasn't really affected the, it's affected greatly what I say to the computer, but not kind of how I say it in terms of typing things in and so on. Probably much more to say about that, but I want to get to some more of these questions here. Let's see. Boy, there's a question from Pranjul here. How can we fix the shortcomings of current neural net architectures? Well, gosh. So first point is, you know, there's this whole area of machine learning, which has become very popular in the last few years. I would say that it really started to become super popular around 2012. And I think its popularity is a little bit, you know, it's flattened off at this point. And there are lots of kinds of things where people said, you'll never be able to get a computer to do that. Like recognize, you know, what kind of bird am I showing you a picture of? And then that's now become pretty easy. How did that work? Well, the way it works is you're using mostly these things called neural nets. And what you're doing is you're showing it a whole bunch of pictures of this kind of bird, a whole bunch of pictures of that kind of bird. And it's kind of learning what these different kinds of birds look like. And then when you show it a new picture of a bird, it's saying, that looks like this thing that I learned before. How does that learning work? What's happening is you're basically trying to translate those pictures that initially get translated into a big array of numbers, each picture. They're kind of like just the colors of the pixels on the screen that represent that picture. And then what you're doing is you're figuring out how to kind of, if you look at all the arrays of numbers that represent an eagle, for example, and all the arrays of numbers that represent a swallow, you're going to what you've got to do is to figure out what's in common between the arrays of numbers that represent eagles and different from what represents, I don't know, a parrot, let's say. There's a fairly efficient method that's now known to try and figure that out. And it's based on neural networks. Neural networks were sort of loosely based on the way brains do things. You know, in our brains, we've got about 100 billion neurons. Neurons are these cells in our brain that basically they either fire and produce an electrical signal every millisecond or every few thousand times a second, or they don't. And they're like either on or off, more or less. They have these spike trains that they produce. But roughly you can say, are they on or are they off? And every neuron might be connected to, let's say, 100 or even 1,000 other neurons. And it's saying, were you on, were you off? And it's looking at the pattern of which other neurons that it's connected to were on and off. And then it's deciding, am I going to be on the next moment or not? And that's kind of how our brains work. And neurons were originally discovered by a microscopist named Ramon Cajal around 1900, looking at actual brains, noticed that there were these cells, these neurons, and it sort of became clear that the brain was this kind of arrangement of connected neurons. Then in 1943, I think, a chap called Warren McCulloch and a chap called Walter Pitts basically figured out this kind of theoretical mathematical framework to describe how neural networks might work. And the big thing they did was to show that given something that could be thought of as a bunch of these sort of objects that were either on or off, and they were connected by sort of wire-like things to other objects that could be on or off, that you could emulate a sort of another mathematical model of a computer, a Turing machine. And you could show that this kind of neural net thing could compute anything that this other model of a computer could compute. At the time, there weren't yet digital electronic computers, but as soon as there were, it became clear that these neural net things could be, well, they could be emulated on a digital computer, and they could in principle emulate what a digital computer could do. People were still very confused about whether brains could somehow do more than digital computers can do, but at least this McCulloch-Pitts model of neural networks was like, mathematically, it's the same story as what a standard computer can do. Well, for a long time, decades, people would use neural nets, and they would use them for various toy things. They would study them, and they would do science with them. And they would try and compare them with brains, and they didn't really compare very well. And they tried to do things with them, and they tried to do early optical character recognition, which went fairly well, of saying, is that an A, a B, or a C as pixels on the screen? And they would try and solve these problems like, is that an eagle or a parrot? And that would fail. And it kept on failing. And back around 1980, I did a bunch of work with neural networks, actually, and I tried to figure out, what did they do? Could they do anything interesting? And I was like, no, they can't really do anything interesting. Well, then in 2011, sort of almost by mistake, it was realized that a sort of a bigger neural net, if you just let it look at a large number of examples and kind of grind around trying to arrange itself internally and grind around for maybe a month of computer time, magically, somehow, the thing would figure out how to arrange itself so that it could correctly recognize those new examples coming in. And so suddenly, at that time, the idea of so-called deep learning, the deep comes from the fact that there are many layers inside this neural net, and they all have to kind of arrange their numbers in order to make the thing work. And it takes a long time to arrange those numbers. You have to go through this whole elaborate training procedure, which can take, sometimes years of computer time, although it can be done somewhat in parallel, so it's not taking quite as much real time, but it can take huge amounts of time to do that training. But the remarkable thing is that it's turned out that it actually works fairly well. It works fairly well on certain kinds of tasks. Basically, when you have a task where it's not really a super precise thing, it's like, is this an eagle? Is this a parrot? Okay, well, it's kind of a clue that you're showing it in a jungle background. It's more likely to be a parrot. It's kind of a clue that the eagle is next to the, the blue sky, whatever. Oh, it gets it wrong some fraction of the time, but it's getting it more or less right. There are many tasks that we humans do where getting things more or less right is super useful. There are other tasks like, I don't know, doing mathematical computation where to get it only roughly right is kind of useless. There are other tasks, plenty of tasks where getting it only roughly right is kind of useless. But in any case, this sort of getting it roughly right thing, and tasks where getting it roughly right is fine. There are lots of them. Image identification is one. Voice transcription, that is, when you talk to, your Siri or something, or Alexa or something, and it figures out what did you say, and it turns that into text, and maybe it sends it on to Wolfram Alpha or something. That process, if it gets some word wrong occasionally, it's not a disaster. And that's another place where neural networks do very well. Similarly, being able to pick things out in videos, that's another kind of place where they do very well. These kinds of things where it's like, well, you get it more or less right and that's good enough, they do very well. And what's really happened in the last few years is that as neural nets get more and more efficient, you can, first you could do single images, then you could do audio, now you're doing video reasonably well. These things, that steadily sort of gets better, and you figure out more and more tasks where it makes sense to get a result that's roughly right. Now, in terms of, will you be able to do magic things? So one thing that gets very popular, that they're usually these little bursts of enthusiasm for different kinds of things. So one that's happening right now is text generation. So you can say, write me a story about whatever, and it will just go and generate the story. Well, it's kind of okay. But if you say, how well did you really do that? What's the way of grading it? You get somebody to say, will this essay get an A, a B, or a C if it was graded as something you send in to, for school or something. But that's not usually done. And usually it's like, well, it's kind of cool. It kind of looks pretty good. But it's really hard to know, did it do great or did it do terribly? And the fact is, it's going to do okay, but I'm not sure that task is a terrific one. There's a version of that task which is language translation, going from French to English or something, where again, it's like if you get it roughly right, that's good enough. Occasionally you're going to get it wrong, but it's still super useful to even get it roughly right. And that's something that's kind of gotten to a pretty good level. It works better when there's more stuff to train the neural network on. So, for example, for European languages, the European Union, for all of its adventures, one thing that it's done is that whenever there's some sort of government document, it gets translated into all the languages that are used in the European Union. So there are these pieces of text that exist in gazillions of languages. I don't know how many it is, 20 languages or something. Is it that many? I don't know, 15, whatever. And that means that if you want to train a computer to say, I want to translate from German to French to English to whatever, I wonder if they're going to drop English. No, I think not. There's still English-speaking countries in the EU. But in any case, that allows you to have billions of words of training data for language translation. But in terms of what will be the kind of the end point of sort of neural net things, it's interesting to figure out, if you could do much better training, what could you train the neural net to do? And there are some additional tasks you can imagine doing. But in terms of, there's some other tasks which have been getting better unbelievably slowly. So one task is conversation. So for instance, back in the 1960s, there was a thing called ELIZA, which was a kind of a sort of fake counselor psychiatrist type thing, where you would type to it and it would say, you would say, I don't know, it would say, what color shirt are you wearing today or something? I'm not sure it would ask those kinds of questions. And it would say, I'm wearing I don't even know what color this is, a white shirt. And then it would be sort of come back and say, does it bother you that you're wearing a white shirt? And it would try and have this kind of conversation. And it used very, very simple rules to do that. People found it kind of fun. And then we kind of go forward, 50 years, and we say, well, what do the conversation systems that we have today, what are they able to do? Well, with Wolfram Alpha, we're able to answer all kinds of questions about the real world. That's a remarkable thing that wasn't clear it was going to be possible. I mean, we did that now 10 years ago or more, and by encoding a lot of knowledge computationally. It's a whole story about how that was done. But that's sort of answer questions about the world. But if it's just like have a nice chat, and do it in a way that really seems intelligent, that's still really difficult. One can have some things that do a good job at a sort of play level, but in terms of really doing it and having a real conversation with content, that's really pretty hard to do, and that's been a thing that hasn't really been achieved yet. I think that in terms of the details of how neural nets work inside. I mean, I can go into arbitrary levels of technical detail about that, but let me not do that. Let me say that I think there are sort of assumptions about how they work that basically make use of calculus in very fundamental ways that probably are neither necessary nor efficient. And there are probably ways of doing things with simpler programs that don't make use of calculus, but they need to make use of new kind of ideas for how you kind of search through a space of programs. And I've sort of worked on those things for years, and we don't really know the answer to how to do that yet. Perhaps we will finally figure that out. In fact, some of the spin-offs from our physics project might be suggesting ideas about how to do that, but we don't know that yet. And that's the kind of, the sort of buzz term there would be things like cellular automata and connecting those to neural nets. There's a very different kind of thing. That's kind of a potential future direction. Oh boy, there's a question from Gis Noesis. How does hitting a bucket of water on the side with a tennis ball make the water surface splash with plenty of tiny droplets that grow very high, but hitting it with the same force with one's foot makes the water move as a big lump which doesn't splash? Is this analogous to the photoelectric effect? Okay, splashes. Splashes are a complicated thing. There was a chap, a man called Worthington, I think, who had a classic book called The Study of Splashes. And that was made possible, a splash. Happens very quickly. So what made it possible to study this was the invention of flash photography. The invention of you have a camera, it opens its shutter, it's, in old days it was exposing film, but then, bright flash of light, it only picks up an image when there's that bright flash of light. And by having that flash of light be very short period of time, you could like freeze a frame. This is all easy to do now, but it wasn't back in the day. You could freeze a frame for 1,000th of a second or something. You could just capture what happened in 1,000th of a second. So you would see things like, bursting a balloon. You would see the little cracks forming in the surface of the rubber because you could freeze that frame by having a very quick flash. And that's the only thing the camera would be sensitive to. So back in, I think, 1908, as I remember correctly, this chap called Worthington made this study of splashes. So what happens when there's a splash? Drop something in water. You drop turns out it matters what shape the thing is that you drop in the water. But let's say you drop a sphere in the water. I think that's the one that's been most studied. You drop a drop of water in the water. So what does a splash look like? A lot of weird things that happen. So one thing that happens is the water goes down and it produces this kind of so-called corona. Looks like a crown. You get this circle of water, and there's a circle and around. So that in the middle, the thing hits the water in the middle, and the water comes up around the sides. And the water seems like it's just coming up in this film, in this kind of crater-like thing that's just uniformly coming up on each side. But it doesn't do that. Instead, the water, which would usually be just this circle of water, it breaks up into little drops, and it forms this kind of crown-like shape where you see the little drops forming around the thing. So you might have 10 drops around the circumference of the circle, a so-called corona effect. And so that's one weird thing. The other weird thing that happens is right in the center of the water's come down, and then the water comes back up. It kind of bounces back, and you'll have this kind of tube of water that comes up, and you'll actually often have a little drop at the top of that tube. It's as if the thing you dropped in had bounced back and made a drop of water. Very weird effects. Okay, what causes these effects? So the main effect that causes this sort of thing that would otherwise be kind of a regular sort of circle or cylinder of water on the outside to break into this sort of crown, what are they called? The things on a crown. What are they called? My gosh. Anyway, the points on the crown, so to speak. The coronets? No, that's not right. I don't know. In any case, not a word that I use very often. In any case, the so-called Rayleigh-Taylor instability that causes causes the thing to break up. Why does it break up? So it breaks up because of a phenomenon called surface tension. And okay, what's the story here? So if you have something like water, water has a certain, the surface of the water will always try to be as small an area as possible. So if you have a blob of water, let's say you're in the space station where things are weightless, so water doesn't fall to the ground, just get some water. What shape does the water make? The water will make a sphere, because the sphere is the thing which encloses a certain volume and has the minimum area. There will be a surface tension that tries to make the water form something which has the minimum surface area. It's a big problem apparently on the space station, that you get these blobs of water that are just hanging around all over the place because they don't fall to the ground; they just blob around there. Anyway, so if left to its own devices, water will, for example, if water is falling in a stream, it will form. It might be falling in a continuous stream, but the stream will tend to break up into these drops as a result of surface tension. And so that's what's happening in the circumference of a splash, is you're forming drops because surface tension is causing this water to, instead of being sort of this continuous band of water, it's breaking it up into these things which are just these little drops. So that's the main effect that causes sort of splashes to be splashy, so to speak, and have all these different pieces, is this instability due to surface tension. I think this question about this question about exactly what shape that you get from different ways to kind of hit a bucket of water or something, those are difficult things to work out. It's only in the last probably 10 years that there's been decent ability to do mathematical models on a computer and work out the kind of configurations that that things like water will make. I mean, and it's still a bit of to what extent do splashes depend on gravity? What do splashes look like in space? I don't fully know the answer to this. I've tried for a while to get some astronauts to really try this out, and they're like, we really don't want to do that, because when you throw a big blob of water at something on the space station, for example, it'll shatter into lots of different drops. And then we have to go vacuum up all those drops. Otherwise, those drops will just get all over the place because they don't fall to the ground. It's not like you end up with a puddle of water on the floor. You end up with little drops embedded in some instrument somewhere, and it's a big nuisance. So nobody wants to have a splash in weightless conditions because you have to clean up a lot of mess. So anyway, that's a little bit of a story about splash. The general phenomenon of instabilities in fluids, it's a fairly ubiquitous phenomenon. It causes all kinds of elaborate things in the atmosphere, in our atmosphere, in the atmosphere of planets like Jupiter. For example, if you look at even a nuclear explosion that's happening really quickly, famous picture from very early, I forget, maybe millisecond, thousandth of a second, maybe less, of the first nuclear explosion, shows this amazing. You might think the nuclear explosion will just go boom and make a spherical sort of object, but it doesn't. It has an instability, and you see these weird shapes that form even after a very short amount of time as a result of a phenomenon a little different. Actually, that's the Rayleigh-Taylor instability, and I may have the other one. The one for splashes might be just a pure Rayleigh instability. In any case, there are these phenomena that cause fluids to become unstable in various ways. And the same thing happens when you have fluid turbulence. You just have a fluid flowing quickly, it's making all those little eddies and so on. That's happening in the same kind of way, but slightly different physics of what's going on. So, question here from Slayer: what sources do you use in keeping up with science news? Oh gosh, I don't know. I'm not. Somehow I seem to hear about things, but I'm not sure I'm that systematic. I think there are a few magazines that I've subscribed to. The one that is there's one nice one called Science News, which is a nice digest of recent science things. But usually there's certain kinds of science where it's like, we saw a new kind of lemur in Madagascar and it looks like this. And that's kind of a who, what, when, where, cut and dried kind of science. It's not, there's this big new idea in some mathematical area. It's more like, this thing happened, we can write about it, it's a story. One magazine that I have to say I've subscribed to for more than 50 years is a magazine called New Scientist. It's a British science magazine. I'm impressed that it's been going for that long. It's a kind of popular science magazine. I always enjoy it because it's full of kind of slightly edgy scientific news. And I have to say, one feature of New Scientist is sometimes it's sort of a little bit the kiss of death for some kinds of science, that if it was written about there, it probably won't become real. And there's a tremendous tendency of articles to end with, the people who describe this say it could lead to such and such a thing. But it's really interesting in terms of just ideas about different random pieces of science that people are exploring, often more outlandish kinds of things. So I certainly enjoy that. I mean, there are much better systematic sources. I kind of have the unfair feature or advantage that I have a fairly large team that I work with, and I know lots of people in the kind of scientific world, and people tend to tell me about stuff that they think I'll find interesting, and I, I'll read lots of things, but I'm not as good a systematic consumer of sort of science news as I might be. Let's see. Okay, there's a question from Kareem saying, 12 years old, how do you set about like doing things like getting PhD in physics by the time you're 20 and so on? Well, I think, a couple of things to say. There's a certain amount of learning the mechanics of how to do science and calculate things and all those kinds of things. I think the most interesting path tends to be, what do you want to figure out? What questions are you trying to ask? You can get a certain distance by just knowing how to answer every exercise in the book. But to go further than that, you have to kind of figure out, well, what exercise would you put there that they didn't think of putting there, or they didn't put there? What question do you kind of find really interesting that you can kind of attack? I would also say that in terms of modern times, tools are really worthwhile things to learn, both intellectual tools and more practical kinds of tools. By that I mean, like, for example, our Wolfram language system, I've spent most of my life trying to, make that the best tool I can for figuring out things like things in science. And, people who know how to program well in that can just do amazing magic things that, that other people are just like, oh my gosh, how did you do that? I mean, I think my youngest son, Christopher, happened to learn programming in that when he was probably 9 or 10 years old or something. He's very fast. He's faster than I am at writing code. And I'm always amused that, what was he showing me just a few days ago? I mean, just all kinds of different things where you just take some piece of data about the world. Oh, that's right. He figured out for the college he's at, he was like, there's a 10-minute job of figuring out, what's the distribution of which courses are being, the correlation between departments and which course is being taught online or not. That's a sort of it's an easy piece of data science if you know how to do it. I think the thing is to understand kind of these tools and be really proficient with them, so that once you have an idea, you can as directly as possible go from the idea to, yeah, I can write a piece of code, type. Then something happens, you get a result, you think about it, and so on, and you kind of iterate, inventing things. That's a sort of really critical thing. I mean, the other thing is kind of more intellectual tools of, what methods and ideas do you learn? In modern times, there's just tremendous, the the strongest paradigm of our time is kind of computation. And just like in the past, it's like learn all those very elaborate mathematical things. Those are cool and those are worth learning. But really being able to be proficient with all these computational ideas, that's going to be the future of pretty much every field, including physics, for example. And I think that the, I would say that in terms of, do you push really hard to do things, to go through school when you're really young? If you can do it easily, sure, why not? But it depends. I mean, for me, I was really interested in doing research and so on, and I got to the point where I was doing that pretty well by the time I was, I don't know, probably 14 or so. And it's like, I can do what I want to do. So let me just go ahead and get to the point of being able to do it, do it for a living, so to speak, as quickly as possible. At the time, I was mostly interested in do physics research. That was the thing I was interested in. And, I think one of the things that's been fun for me in the rest of my life, so to speak, has been I've been interested in just so many other kinds of things. And, it was really good to get to the point where I could, climb a fairly tall tower of doing physics research. But then, by golly, I've learned about a zillion other fields since then. And that's been a lot of fun. And I think it's, in the end, even my big effort in physics in recent times has been made possible because I've learned all these other things. And now those things can come back to inform what I'm doing in physics. So, I think that for me at that time, I was like, I'm mostly interested in just this one thing of doing physics research. If I'd been interested in lots of things, I probably would have found it really good to just hang out in school for a long time, just taking classes in this and that and the other thing, and just learning all kinds of things. But as it was, I kind of definitely knew I want to do this. Okay, fair enough. By the time I was 20, I was like, okay, I'm now, playing physics professor or whatever. And what am I going to do next type thing? And I did figure out a little bit of an answer to that, which was good. I think that, but as it was up to that time, I was very, very, very focused on this one kind of goal. And I think that if you're set up that way, then by all means, go do it. If you're like, well, I don't really know if that's the goal, if I want to learn these kinds of things, you kind of have an opportunity when you're young to just like learn all kinds of stuff, and nobody's really going to ask you, why are you doing that? Why are you learning about this and that and the other thing? It's just like people expect young people just go learn about all kinds of things, and you kind of have a free pass to go do that. When you're older, it's not so easy to spend a bunch of time learning about things. I mean, I kind of have a sort of a cheat way to do that, which is I run a company that applies computation, builds tools that apply computation to everything, which means I kind of have an excuse to learn about pretty much anything. And I've made use of that I've made use of that and chosen to learn about all these kinds of things. But that's something not every, that's a rare kind of job that kind of lets you have the excuse, oh, I'm going to learn about chemistry today. I'm going to learn about, something about, molecular biology today. And those are things that are actually important and contribute to sort of the real work that I'm doing. Let's see. I need to go soon here. Well, there are questions here, and maybe I should do a different one of these kinds of sessions. There are questions here from Parmenides, great screen name, about various kinds of history questions. And I realized that I probably should do some history Q&A, which perhaps will be less interesting to the young and more interesting to older. There's a question about a course at MIT that I've not heard of, so therefore I think don't know about it. And you ask about Dana Scott. I actually happened to hear from him the day before yesterday. So there's lots of things. Let's see. Somebody, and this is indicating that we don't just have kids on this live stream. Rohit is commenting, the first computer he programmed was a PDP-8. That takes one back a bit. Cool, though. Um, okay, there's a question here. I'm just going to answer a couple more from Ozan. Why is computational science not spreading among high schools better? Good question. Good question. You know, there have been multiple waves of people trying to sort of teach computing in schools, starting in the 1960s. You know, BASIC was a language that's actually pretty good that was invented for teaching kids. Logo, another language. Logo kind of became Scratch. You know, various other efforts. Here's what happens. You know, and we've been involved in this, and I think we've been able to do some really interesting things because with Wolfram language and with our whole computational language sort of development, you can get to the point where you just use computation as a tool to do whatever you're interested in. You know, you're interested in I don't know, geography, you can use it because we have all this data about geography. You can immediately study, you know, questions about geographic questions about, you know, which country has the largest lakes, or, you know, who knows what it is, which, you know, which country has, which region of the world has the most red in its flags, or, you know, all these kinds of questions. Or you could answer a question, you know, if you're interested in, I don't know, in chemistry, you can answer some question about that. And this is part of, you can just do this computationally. And that's uniquely become possible with the things I've been building over the last third of a century in Wolfram language. That's uniquely something that's possible with our language. What has happened is, and there's plenty that's being done with sort of teaching computational thinking and so on with our language. And for people who are interested, like there's a little book that I wrote, and it's a MOOC and things like that, called Elementary Introduction to Wolfram Language, which is a good place to start on those kinds of things. You know, that's a really good idea, and it works really well. And I have kind of a hobby project of actually trying it on the ground with actual kids every week, actually. That's my way of finding out whether I know what I'm talking about whether this really works with kids, and it works really well. Recently, I seem to have ended up, it's a little bit harder to do in a Zoom setting than it is in person, but it works really well. And people get to explore all kinds of really interesting things, and just using computation as a vehicle for exploring things they're interested in, not its computation as a means in itself. It's a little bit like when you learn writing. You know, you can just do classes where you're just learning to write, you know, learning to write English or whatever. But at some point you have to start writing about things, or it becomes kind of boring. It's like, how many exercises can you do where you're just abstractly writing things? You have to start writing about things. Well, you know, kind of the whole point of sort of having a computational language is it gives you a way to do computation about things. And then you can do all kinds of cool stuff. And that's a really good thing to do with kids, by kids, et cetera, et cetera, et cetera. Okay, but then people get the idea. We've heard computing is important. We've heard that programming is what you do when you do computing. What is programming? Programming is writing those instructions that tell a computer what to do. Oh, you know, you use a programming language to do that. The programming language has variables and loops, and it has this and memory locations, all that kind of thing. Well, that's a very different activity from using computation to think about how you solve a problem, and having the computer automate away all of those things about where's the memory location, how do I allocate, you know, how do I loop over this set of variables, things like that. So, but what people then think programming and computing is this very low level thing that's like, how do I set variable values for variables? How do I jump to this part of the program? All that kind of thing. Okay, that activity is very fiddly and to many people very boring. And I think that, you know, I've written, you know, it's the whole point of having a computer, I think, is to let the computer do as much as it can for you, rather than you kind of coming to it and saying, I'm going to tell you exactly step by step how to do your thing as a computer. It's like, you have an idea. It's the job of the language designer to let you, as directly as possible, express your idea so that a computer can help you with it. And that's kind of what I've spent a large part of my life doing. Really, no other group has been doing this. This is sort of our unique thing, is this idea of building this sort of full-scale computational language to express things computationally. It's always better, it's always easier to explain to people when you say, there are 5 things like the thing that we've built, but there aren't. It's just this one thing. And, but that allows you to do this thing of sort of thinking computationally and using the computer as your kind of assistant to explore the world, so to speak. Very powerful thing to do. What people end up doing is teaching coding, which ends up being, let's, tell a computer at a low level what to do. Okay. Do people care about that? Some people like it. Some people like it a lot. Some people are going to be programmers. And that's fine. And the world needs a certain number of those people. People like me try to automate the things which are kind of boring to do so that you can do the interesting things that only, where it's a human telling the computer what to do and the computer is automating doing all the details, so to speak. But it's like, so it's kind of a question of when you're teaching something, how far back do you go? If you're teaching something like, I don't know, well, it comes up with math as well. But I mean, if you're teaching writing, do you explain to people, this is how you create a pen? This is how you take a feather and slice it and put it in ink to make a pen to write with? Well, no, you can just assume you have a writing implement and you're just going to write stuff. Or, if you, there's a question of where do you start from? And this kind of going backwards and starting from this very low level things that are indeed what professional systems programmers, do is probably not the best thing to be teaching kids. So a lot of kids find it kind of dull. And what's happened, like with math education, a lot of that has become very mechanical and people find it kind of dull. And it's a shame because math is really, really interesting. And I think it's really interesting. At least I think a lot of people would find it much more interesting and much more compelling if they weren't in the details of let's mechanically do something that actually we could get a computer to do much better. So, I think one of the problems is that sort of the coding type thing tends to be kind of boring, kind of mechanical. We are now in about the 5th iteration of people trying to teach coding in schools, and it seems to never really quite work. It's also the case that, to what extent should learning computational things be like people typically learn, I don't know, musical instruments or something, not as part of the systematic schooling story, but as rather as a kind of avocation separate from that, and to what extent should be part of the main sort of schooling thing. There's also issues like, I think the things that we've built with this kind of computational language, they should allow one to really bring computation into education. But in the same kind of way that writing is brought into education, not as something where it's all a writing class, but writing is just something you do as part of other things that you're learning about. And I think there's a certain level that you have to get to with sort of writing, and there's a certain level you have to get to with computational language so that you can go and use it for other things. But that's kind of the pattern that should be followed. And that will really work. And one of these years, one of these decades, that's how people will learn. It's kind of interesting because, we basically, I've been involved for a long time in building the technology for this. The mechanics of how you actually inject it into the school system, that's a big, complicated mess because there's a complicated ecosystem of, if you're going to put in a school, there's lots of things kids have to learn because after all, there are these exams they have to take and the exams test them on this and that and the other. And, this isn't something the exams test them in. But you say, well, why aren't there exams that test them in this? Well, that's because people aren't learning this yet. So it's a kind of chicken egg complicated cycle. In some countries, that cycle has been more successfully kind of broken. I mean, one of the things that's a little bit shocking to realize is, public education, where there's a sort of the government provides educational for people is 100 and something years old in most countries. Some a little bit less, some a little bit more, but it's about 100 years old. Maybe 140 years old, maybe. So one of the things that's really interesting is this idea of computation. It's the first really fundamental, really broad idea that has come into existence since the beginning of public education. So, everything else, reading, writing, arithmetic type thing, they all existed before, when public education was first invented. But computational thinking did not exist at that time. And the question is it possible? Is it even possible for something new to be introduced into something that's had this century-long kind of sort of development? One hopes so. Otherwise, it's people learning things sort of independent of school. I mean, one of the things to realize, that people may know this, but many of the hotshot programmers out there, they didn't learn to program in school. They just learned to program. And it's not, they didn't take a class in it. They took no classes in it often, but they're really good programmers, and they built really big systems and so on. But it's something where it's like, what you do in school is not necessarily that connected to what you're able to do, as a practitioner of these kinds of things. All right, I think I have to wrap up here. Thanks for dropping in. I think we've been, I say we, my team has been chopping up some of these Q&A sessions and turning them into podcasts. So if you're interested in questions other than the ones we talked about today, you might find some of them answered in some of those podcast episodes. All right, well, thanks for coming, and see you next week. Bye.